Hello friends, Um I will be doing polymers here. The chapter is primarily taken from NCERT curriculum and it would serve for both giving the board exams as well as for the competitive exams. I would be taking up MCQs in between and would also explain you how to solve these MCQs. This is the entire chapter would be covered up in about 4 different lectures, and this is the first lecture in which I would be talking mainly about the basic definition and the classification. The term polymer is formed by two Greek words. There are two Greek terms involved here. Poly means many and mer means parts or units. Thus, polymers have, these are big molecules in which there are many units which are, coupled up together, right? Let us give the definition of polymers then. So the basic definition goes like this. All right, so definition is a macromolecule formed by chemical combination of large number of repeating structural units, which are then called monomers. So any polymer would be a macromolecule, and this macromolecule is formed by chemical combination of large number of repeating structural units. These repeating structural units are called monomers, and you know that these monomers, they are held together in any polymer by covalent bonds, right? Now you can even put it like this, that the phenomenon by which a polymer gets formed from monomers, now that phenomenon is called polymerization, right? So you must be wondering what should be the approximate molar mass of any polymer. Now, we cannot always give a perfect molar mass or a perfect range of molar mass. So we have this very broad range given. The molar mass of polymers molar masses of polymers range from 10 raised to 3 to about 10 raised to 7 U. So these are really big molecules, right? And we generally call them as, macromolecules, right? I would give you first of all an example of how this happens. For example, when large number of ethene molecules, ethene is this, when large number of ethene molecules have to take N number, and they undergo polymerization, you get a huge polymer, right, which is then called, this is N times, this is then called polyethene. So this is polyethene, and this is ethene, right? You can see that here only one type of monomers form the polymer. So when only one type of monomers they form the polymer, we call this as a homopolymer. So this is also called a homopolymer, right? Many times you find that there are two different types of monomers which undergo polymerization. Now here there's this molecule which is like NH2, and then we have 6 times CH2, and then NH2. This is also called hexamethylene diamine, or HMDA. We would be talking about more of this. So if you take n molecules of this and you take n molecules of COOH, CH2 4 times, and COOH. This is hexane 1,6-dioic acid, and it is also called adipic acid. This is the general term which is used for it, and here you have this N molecules. Now here there is this polymerization taking place. And I write polymerization, where water is lost and there is about 2n minus 1 H2O lost. See, what happens is here you have H going out and here you have OH going out, and that is how water molecule is lost from this side as well as this side. For this molecule, water, OH is lost from this side and OH is also lost from this side. So per one molecule of this and one molecule of this actually reacting and forming the skeleton, you find that there would be two water molecules lost, one from this side and one from the other side, right? So every molecule that participates would lose two water molecules in order to make the polymer. There are n molecules taken, so it should be 2n number of water molecules produced. But when the polymer gets formed, you find that, there would be the entire chain would have at least one CH2 at one terminal, one NH2 at one of the terminals, which would not be, undergoing any condensation reaction. And there would be one COOH, which would also not undergo any condensation. So you find that this is what you get. You find that when this chain ends, there would be one NH2 left, just like that. And when this chain ends, there'd be one COOH left, just like that, and would not, undergo condensation. So ideally, one water molecule less. So it's not 2n, but 2n minus 1, right? And this is, the amide linkage that you see. So such molecules are also called polyamides. This is in particular a nylon. The name is nylon 6,6, because each monomer here, this and this, gives 6 carbons in the polymeric skeleton, right? So you find that both the monomers, they give 6 carbon each for making this polymer. So it is 6 and 6, right? 6 provided by one monomer, 6 carbons provided by another monomer. So it is 6 and 6. This is also called, in general, it is also named as polyamide. That's because the amide link gets repeated. So, and you can see that here two different monomers react and give you a polymer. So this is also called a copolymer. What is it called? Copolymer. I may not put this, I can directly put this. So now, when same monomers form the polymer, it's homopolymer. When different monomers undergo reaction and form a polymer, it is called copolymer. This is called nylon 6,6 because each monomer contributes to the polymer in giving 6 carbons. And once again, there'd be 2n minus 1 water molecules removed, right? So these are two different types of polymers, the examples. I was also talking about one very important thing, and that is the difference between macromolecules and polymers. So you also have to know the difference between the term macromolecule and the term polymer. Let us understand that. There's this very important statement given here that all polymers are macromolecules, but all macromolecules are not polymers. See, all polymers have huge carbon skeletons and they're very big, and so they all can be called, ideally called, macromolecules. But there are a lot of macromolecules which have huge molar mass. They are very, very big, but they do not have repeating units like polymers. Polymers have repeating units, and a lot of these macromolecules, they can be big, but they cannot have repeating units. And I give you some examples. So I say macromolecules which are not polymers. I'll give you these examples. One is like lipid. A lipid is a macromolecule, but it would not be a polymer. Then hemoglobin. Again, a huge molecule, macromolecule, but not a polymer. Doesn't have a proper repeating units. And then you also have chlorophyll, which is also not a polymer. It is a big molecule, it is a macromolecule, but not a polymer. So let us now go to the classification of polymers. There are about 4 different classifications given for polymers, and I'm going to start with the first classification. This is the classification based on source of polymer. So let us take up the first one, classification based on source. There are 3 important types of polymers right here in this category. The first type of polymers that you find are called the natural polymers. These are the polymers which are found in the bodies of plants and animals, and they exist naturally. So found naturally in bodies of plants and animals. Example, you have proteins, cellulose, starch, etc. Right? The second in this category would be semi-synthetic polymers. These are the ones which are formed by chemical modification of natural polymers. So here we write these are formed by chemical modification of natural polymers. Example, cellulose acetate, vulcanized rubber, cellulose trinitrate, etc. You know that cellulose acetate is formed by acetylation of cellulose. Vulcanized rubber is formed by taking natural rubber and vulcanizing it, and cellulose trinitrate is obtained by taking cellulose, natural cellulose, and then performing nitration on it. Now, the third is like the synthetic polymers. In synthetic polymers, we say they are man-made polymers. These are man-made polymers, and you find some of the examples. You have nylon 6,6, we've already done this. Then we have, polyethylene, which you all know. Then there is something called Buna S. Then you have Buna N, etc. These are out and out man-made polymers. So the first type of the first category in classification based on source. Based on source, there can be 3 different types of polymers. So here we have used different ways by which we can classify polymers. The first method we use is like classification based on the source of polymer, in which we have natural polymers, semi-synthetic polymers, and synthetic polymers. Okay, the second classification is classification based on structure of polymers. In this case, you have polymers divided into 3 categories. Once again, the first one is like linear polymers. This is very simple and easy to do. Linear polymers. These are the polymers. In these polymers, monomers combine to form linear chains of polymers. Basically, the chains of polymers are not branched, they are very, very linear. So now what exactly would happen because of this? So these polymers, they are linear. So you find that, suppose this is one chain of polymer, the second one, the third one. Basically, because they are linear, right, they can, generate very high density. The chains can remain really close to each other and hence generate a very high density polymer. Melting point is always, quite high. And examples: polyethylene, polyvinyl chloride, which we call PVC, etc. So these are linear polymers. Here monomers combine to form a linear polymeric chain. So these chains, different polymeric chains, they can really remain close to each other. So such polymers are always high density. They also have very high melting points, etc. Branched polymers, that's the second one here. As the name tells you that it's a branched polymer, right? So here, polymeric chains which are formed have branches. So the polymeric chains have branches here, right? And you have to know that because of these branches, their density is low, as the chains cannot form a closed packed structure. You also find that melting point is low. And some examples: low density polyethylene, you also have, let's say, glycogen, etc. These are all branched structures. If I have to give a pictorial form of branch, I can show it like this, that this is one chain and this is another chain, and you may have some branches which are periodically formed, and hence the chains cannot come close to each other, right? So branched polymers will have chains not coming very close to each other, and they would not form a close packed structure. So density is low and melting points also are comparatively less, right? Now cross-linked or network polymers, right? Now this is a very special case, you must know this, that here the monomers are bifunctional or trifunctional. Monomers are bifunctional or trifunctional. That is one thing, which means they may have two functional groups or three functional groups or more. And in this kind of polymers, there are strong covalent bonds formed between polymeric chains, right? So this is something which you have to know, that here we don't have branches. This is, let's say, I'm going to draw the polymeric chain. This is one, this is another, this is third, and now you may have that there would be some connections in between, right? This is what we call as the cross-linking. Example, bakelite, melamine, etc. So the third type of classification is based on mode of polymerization. So what do we mean by mode of polymerization? It is like the way polymers are formed here, the type of chemical reaction which is involved in making of polymer, right? That's called the mode of polymerization. So here there are two different types of polymers. One, we call them as addition polymers. Now these addition polymers, they are generally formed by addition of monomers. So here I may in short write formed by addition reaction of monomers. So because when monomers have to undergo addition reactions, they must have pi bonds in them. So monomers have multiple bonds in them. Multiple bonds could be like a double bond or a triple bond, right? And I'll give you some examples. The first example would be like when you find that there'd be n molecules of ethene, right, undergoing polymerization. You can see that in addition reaction, the pi bond breaks and two new sigma bonds are formed. So here the pi bond would break between two CH2s, and you can see that there are two new sigma bonds formed, right? So for every one pi bond that breaks, there would be two new sigma bonds formed, right? One pi bond breaks and two new sigma bonds are formed. Yeah, and this is like a polyethene, and as you all know that this is a homopolymer. You may even have two different types of monomers participating here. Let us take up this. So this is what we have. This is n molecules of this treated with n molecules of C6 H5 CH double bond CH2. Now here we have, so this is then called butadiene, and this is vinyl benzene or styrene. Now the polymer which is formed here goes like this. It's CH2 CH double bond CH, double bond CH, CH2, and then we have CH2 CH, and then you have and then there is this benzene ring PH C6H5 n times. This is called styrene. This is called styrene butadiene rubber, also known as SBR, styrene butadiene rubber. This is, as you can see, that there are two different monomers combining, so it is a copolymer, addition copolymer. You must be wondering how this molecule undergoes addition reaction. So let me show you the arrows at least, so that you can figure out how this goes. So for that, you have to first of all put everything up like this, and you have to put your CH2 double bond CH, and this is your styrene, right? This is in, this is in. Now let's see how the arrows go. See, it's like one arrow, so a bond coming in at this carbon and forming a bond, and then you have this bond going here, this bond connecting here, and this bond going forward, right? So this goes forward and it actually combines here. So now how do I get the polymer? CH2 CH double bond CH, CH2, one more CH2, and then CH, and then we have this is SBR. Yeah. Now the second in this category is condensation polymers. We've seen addition polymers. Now we have the condensation polymers. Now what are these condensation polymers? Here, as the name tells you, that they are formed by repeated condensation reactions of bifunctional or trifunctional monomers. Basically, monomers, they undergo condensation reaction, right? And here you may even say that as polymers, or as monomers combine to form polymers, as monomers condense, small molecules like water, HCl, ammonia, an alcohol molecule, etc. are simultaneously lost, right? And as I've told you that they can be of two types. They can be homopolymeric type, or they can be copolymeric. A copolymeric example of a copolymer, condensation copolymer, I've already given you. For example, when you take up your hexamethylene diamine, it's like hexamethylene, 6 times methylene, diamine. This is called HMTA. And you take N molecules of adipic acid, the same molecule, and now when you allow them to undergo condensation or polymerization, I can give you that there'd be like 500, and the reaction takes place at about 525 kelvins, and 2n minus 1 water molecules are lost. So minus 2n minus 1 water molecules, and this is going to give me nylon 6,6. It's a polyamide, and it is also copolymeric in nature. So this is like, nylon 6,6. And this is basically a copolymer. This is basically a copolymer. So I think this is an example of a copolymer that we have. Now I'm going to give you an example of homopolymer, right? So just a second. So here we have the example of homopolymer, which is formed by condensation reaction. Yeah, the first thing that happens is like hydrolysis. This is caprolactam here. Caprolactam is a cyclic amide, and that is where the reaction begins, where the bond breaks here, undergoes hydrolysis. This hydrolysis would give us a zwitterion, right? And N molecules of zwitterion are formed if you take N molecules of caprolactam. And then you can have, a zwitterion which undergoes condensation to finally give you, nylon 6. Because there is only one monomer, we call it as nylon 6. And that monomer gives us, 6 carbons. This is also a polyamide. This is also a polyamide. And it should be homopolymer. Right? So we have the two things. The first one here is a copolymer. The second one is a homopolymer. So here we have the nylon 6,6, which is a copolymer, nylon 6, which is a homopolymer. Okay? So you need to know this. Now we move on to that fourth classification, and this is the classification based on molecular forces. So this is the fourth type of classification. This is based on the molecular forces. Molecular forces would mean the kind of interactive forces that polymeric chains have in between them. Mechanical properties of any polymer depend on interactions between various polymeric chains. Now, when I say interactions, what kind of interactions would be present in these polymeric chains? Let me tell you that. The kind of interactions present would be dipole-dipole type of interactions, simple van der Waals forces, hydrogen bonds, etc. So there are various types of interactive forces present between the polymeric chains. Their mechanical properties would depend, the mechanical property of any polymer would depend on these forces. And based on these forces, we have 4 different types of polymers here, right? So let us take up these 4 different types of polymers now. This is based on the molecular forces or the attractive forces between the polymeric chains. So we take up the elastomers first. As the name tells you, these are rubber-like solids, right? And it has been found that they have the weakest intermolecular forces. They have the weakest. Ideally, they have van der Waals forces. And this is the weakest type of force that you have. They have a random coil-like structure, which can, and this is like irregular in shape. This is what we talk about the polymeric chains. When I say random coil-like structure, it is like the random coil-like structure we have with polymeric chains, and they have irregular shape, right? Now, on application of force, the chains, polymeric chains, can stretch up to 10 times their original length. Ten times their original length, and upon removal of force, they get back to original coiled structure. Again, see, basically these chains, right, they have only van der Waals forces in between them, but at a few points, right, these chains have some cross links. So these long polymeric chains of elastomers have some very few cross links, because of which they can retrace back to their original coiled structure when the force is removed, right? And now we just have to do some examples. So I can put up some examples. Buna S is a rubber. Buna N is a rubber. You can even have vulcanized rubber. Etc. So all these are elastomers, right? So yeah, this is the first category, elastomers. Okay, the next category here is fibers. Now fibers, they have the strongest intermolecular attractive forces. Generally, the polymeric chains have attractive forces in form of either dipole-dipole interactions or H bonds. The second in this category, is like when you have fibers, they have very high tensile strength. They are very strong. High tensile strength, high melting point, and least elasticity and very low solubility. They are insoluble in most of the solvents, a very low solubility. And now you can give some examples. You can give examples of nylon 6,6. This has intermolecular H bonds. And you can even have polyester, any polyester. This would have dipole-dipole interactions. So all this, right? So this is about the fibers. These are the polymers which are the strongest and have the most highest melting point or very high tensile strength, and the attractive forces are also very, very strong. H bonds or dipole-dipole interactions. Okay, examples are nylon 6,6 or polyester. The third type of polymer that we put in this category is thermoplastics, and here we say the intermolecular attractive forces are between elastomers and fibers. So basically, the attractive forces are between the elastomers and fibers. So yeah, generally these are the polymeric chains are linear or slightly branched. These solids become soft upon heating and again become hard upon cooling. They become soft upon heating and again become hard upon cooling. So basically that, right? And yeah, hard and rigid when you cool them. So what is the advantage of having this property? The advantage is they can be molded into desired shapes. And remember, this can be repeated n number of times, right? They can be remolded. They can be remolded n number of times without affecting their physical or chemical properties. All right, and then we have the last part, and that's the examples. Polyethylene, polyvinyl chloride, which is like PVC, etc. Okay, so this is about your thermoplastics, and now we have only the last part left, the last category of polymers left, which are called thermosetting plastics. See, before we start with thermosetting plastics, there is one small thing that you all need to know, and that is plasticizers. What are plasticizers? You have to know them. These are the chemical substances, right, which are generally added in order to make a thermoplastic more soft, right, when it is heated. So, these are those thermoplastics which do not get soften easily are added with such organic compounds. These are plasticizers, right? And these compounds are then called plasticizers. Example, you can give example of dialkyl phthalates, tricresyl phosphates, etc. So these are plasticizers. Okay, so you need to know this. So thermosetting plastics would come the next in this category. What are thermosetting plastics? These are semi-fluidic substances right? They have low molar masses. When heated in molds, see, molds are generally used for making different things and different plastic things with different shapes, etc. So when heated in molds, they undergo extensive cross-linking. So these polymers are also called cross-linked polymers, right? To form, once the cross-linking occurs, it forms a hard infusible mass, a hard infusible mass, a three-dimensional network solid is thus formed. And examples you can give: bakelite, melamine, etc. So this is now the last part, and this is thermosetting plastics, and this is like the last part. So we've done 4 different ways to classify polymers. This was the 4th method of classifying polymers. This method was based on classifying polymers on the basis of molecular forces of attraction that they have, right? So that is all. Now we would then uh, go to the next video then, and in that video I would talk about the types of polymerization, which means the way polymers get formed, the general chemical reactions by which they get formed.